Hello, welcome to AP Calculus Lecture 5.6b, where we're going to be modeling population growth. We're also going to be talking about some other models that use exponential models. So let's start with the derivation of the population growth model. So if we are to start out with the change in population over the change in time is equal to some constant times the population. We want to separate the variables, so we're going to multiply both sides by dt and divide both sides by p. So we'd have dp over p is equal to k dt. Now we're going to integrate both sides to try to get to a model equation. So we would have, if we integrate dp over p, you're going to have the natural log of p is equal to, of course you could bring that k out front, and the antiderivative of dt is just t. So you would have kt plus c. So we want to get this into the form of a p, or p of t. So we exponentiate both sides. So let's exponentiate those two sides. Now, this would cross out, right, the e in the natural log, and you'd have p of t is equal to e to the kt plus c. Now, just like in the previous section, we can rewrite that as e to the kt times e to the c. So at population times 0, that's our initial population, p of 0, is going to be e to the 0 times e to the c. Well, e to the 0 is just 1. So we would have population at time 0 is equal to e to the c, which we're just going to call as c, or p sub 0. When you're dealing with population, we like to call that p sub 0. So that gives us our model. P of t at any time t is equal to c, or p sub 0, times e to the kt, where this is our constant. This is initial population. K is our modeling constant. And when we work some of those problems, you'll see how we get that. And then t is time. So this is our basic format. P naught times e to the kt. So we'll write it cleanly up here. This is what you need to really memorize. P of t, when it's exponential population growth, is P naught times e to the kt. Okay, so I'll leave that there. Pause the video if you need to, and we'll work on population growth problem. Okay, so our first example is, suppose a pond has a population of bacteria of 1,000 of this type of bacteria. Every 2 hours, the population doubles. Write an equation to model the growth of the bacteria population. Okay, we have an initial population of 1,000. So using this, we would have P of 0 at time 0 is equal to 1,000, our initial population, times E to the KT. Now P of 2, so at 2 hours, we know that the population doubles, so it's 2,000. So we can then fill that in. P of 2 is 2,000, so we would have 2,000 is equal to 1,000 E to the KT. So if we divide both sides by 1,000, I'm going to have 2 is equal to E, and the T, excuse me, is 2 hours, right? Time is 2 hours, so every 2 hours. So I have 2 is equal to E to the 2K. Now we can solve for K, we can get that constant by taking the natural log of both sides. Natural log of 2 is equal to the natural log of E to the 2K. So we would have the natural log of 2. We can bring that 2K out front using the properties of logs times natural log of E, which is just 1. So K is going to equal the natural log of 2 divided by 2. So if we get out our trusty calculator, we would have the natural log of 2 divided by 2. Natural log of 2, and then divide that by 2. And we'd have 0.347 if we round to 3 places. You want to go out at least 3 places, maybe more. So K is 0.347. So the answer would be P of T is equal to 1,000, our initial population, times E to the KT, 0.347 times T. So let's check this. We'll test it out. We know that at 6 hours, that means it's gone from 1,000 to 2,000 at 2 hours, 2,000 to 4,000 at 4,000, 4,000 to 8,000. So the population should be 8,000. So let's check that out and see what P of 6 is. It's going to be 1,000 times E to the 0.347 times 6, and it should be 8,000, or really close because we did do a little bit rounding here. Okay, so I would have 1,000 times E to the, I'm gonna do 0.347 times 6, and you get 8,020, which that's approximately equal to 8,000. So pretty close. I did round that quite a bit. Let's do 1,000 times E to the, and I'm gonna go up here and do the unrounded version, times 6. You see that's 8,000, almost 8,000 right on the dot if I don't round. So yeah, we could do a test there and see that our model is correct. All right, let me clear the board and we'll work some problems from the book. So if you want to turn to page 363, we're going to work number 28. All right, so 28 is about radioactive decay. So let me bring that problem into view. So we have carbon-14 dating assumes that the carbon dioxide on Earth today is the same radioactive content as it did centuries ago. If this is true, the amount of C14 absorbed by a tree that grew several centuries ago should be the same as the amount of C14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much of the radioactive carbon as a piece of modern charcoal. How long was the tree burned to make the ancient how long ago was the tree burned to make the ancient charcoal? And the half-life of C14 is 5,730 years. So what half-life means, that's just the time it takes for half of the mass to decay. Or a radioactive mass is going to eject its mass, all right, into the atmosphere. So for half the mass to decay, or just you can think of it, just goes away. So our model will be something like this. Y is equal to CE to the KT, where Y is equal to the current mass, C is equal to the initial mass, K is of course a constant that we might have to figure out, and then T is time, usually in years, but it could be just minutes or seconds, depends on the situation. We know that we have a half-life of 5,730 years. And so what that means is that at half-life, Y is 1/2 of C. So that means Y over C is going to be 0.5. So we could say that 0.5 is equal to, because Y over C is 0.5, E to the K times 5,730 years. So I can get K for this substance, knowing the half-life, knowing the time that it takes for half of the mass to be lost. So we'll take the natural log of each side. Now I can bring that 5730K out front. Using properties of logs. So that's just 1. So K is the natural log of 0.5 divided by 5,730. All right. So we have the natural log of 0.5 divided by 5,730. All right, that's negative 0.000121 is what I'm going to round that to. You can change, I'm in scientific notation, but you can turn that off going into mode. 0.000121. So I want to round it to at least 3 non-zeros. Okay, so now we want to know how much mass do we have, how much is left when we only have 15% as much of the original mass. So in that case, y over c is not 0.5, it'd be 0.15. Now, it's negative because it's losing mass. If it were positive, it would be gaining mass. All right, so we would have 0.15 is equal to e to the kt. That's minus 0.000121. We use the half-life to get k. And then we want to know, excuse me, I misspoke a minute ago. We want to know how long it takes to get to 0.15%. Well, we know it's going to take longer, a lot longer than 5,730 years, because that's how long it took to get to half its mass. We're going all the way down to 15% of its mass. Okay, so I'm going to move this up here. So let's take the natural log of both sides. And then we'll use the properties of logs. Natural log of 0.15 is equal to negative 0.000121t times the natural log of e, which just goes to 1. So t is going to be the natural log of 0.15 divided by negative 0.000121. Well, I know that the natural log of any number less than 1 is going to be negative, so the negatives will cancel. You can't have a negative time, so you know you've made an error if you've done that. So we'd have the natural log of 0.15, divide that by negative 0.000121. 121. That's 15,607. I'm going to round that up. 15,679 years. So that makes sense. It's a lot more because you're losing a lot more mass. It's a lot more than 5,730K. Getting close to triple that. That time to get all the way down to 15% left. All right. So let's use this type of problem solving to work some problems involving money, compounding interest. All right, so our next example from the book is example 30 on page 364. Okay, so let me bring that into view. So it says, complete the table in which interest is compounded continuously. We start with an initial investment of $20,000. The annual rate is 5.5%. We want to know how long does it take to double, and then how much will you have after 10 years. Okay, so from the last section, hopefully you remember, our continuous compounding formula is A, our accumulated amount, is equal to P times E to the RT. All right, where A is the amount at time T, P is the initial investment, R is equal to the interest rate, and T is time. And with these, it's definitely going to be in years. Okay, so our table says our initial investment's $20,000. So if we know the time to double, or we want to get the time to double, and we have the rate, we know that the doubling amount would be $40,000. So this is part A. So $40,000 is equal to 20,000 e to the r 0.055 times t. All right, sorry about squishing it in there. So divide both sides by 20,000 and you'll have 2 is equal to e to the 0.055 t. Let's take the natural log of both sides. The natural log of 2 is equal to the natural log of e, 0.055 t. Now we can use the properties of logs to bring that 0.055 t out front. That goes to 1. So t is equal to the natural log of 2 over 0.055. So we'd have the natural log of 2 divided by 0.055. And that is 3.59. Let's see. Log of 2. Oh, excuse me. Natural log of 2 divided by 0.055. All right. There we go. 12.6 years. So you can see I accidentally had the 0.055 as part of the natural log. So that's time to double. And then part B is how much will you have after 10 years? So after 10 years, A is going to be 20,000. So you just plug in here. E to the 0.055 times 10. All right, so 20,000 times E 0.055 times 10. And that is $34,665. All right. Okay, let's look at number 32. And I'm going to have to clear the board here. So 32, we want to find the rate and the amount after 10 years. Okay, so in order to find the rate, we know the time to double is 5 years, right? So we would have 20,000, because we're starting with 10,000, E. We don't know the rate, but we know it took 5 years to double. So if we divide both sides by 10,000, we have 2 is equal to e to the 5r. So the natural log of 2 is equal to the natural log of e to the 5r. Natural log of 2 is equal to 5r natural log e, which goes to 1. So the rate is the natural log of 2 over 5. All right, so putting that into your calculator, you've got 0.1386. So you need to multiply that by 100 to get it to percent, so 13.9%. So that's part A, and then part B is the amount after 10 years. So we have A is equal to 10,000 times E to the rate 0.1386 It's 86. We'll go ahead and round it 0.139 times 10. So that's 10,000 times E. So the 0.139 times 10. And I get $40,149. Just rounding that a little bit. Okay, one more example, not using the continuous compounding formula. We're just going to use the standard compounding formula. Sorry about the length of this lecture, but so the compounding, which you've had to learn this before, the non-continuous compounding formula. So that is A is equal to P times 1 plus R over N to the NT. And N is equal to the number of compoundings per year. And the other variables are the same as the continuous compounding formula. So let's take a look at number 38. And we'll just do a couple of these. So 38 says, if you read along, find the time necessary for $1,000 to double if it's compounded annually, monthly, daily, and continuously. So let's just do annually and daily. So part A. So the time to double. And we're starting with $1,000. So if we doubled, we'd have 2,000. 2,000 is equal to 1,000 times 1 plus the interest rate is 6.5%. So 0.065. If it's compounded annually, that's 1. So N is 1, and we want to solve for T. So if I divide both sides by 1,000, we would have 2 is equal to 1 plus 0.065 to the T. So 2 is equal to 1.065 to the T. We'll take the natural log of both sides. So I'd have the natural log of 2 is equal to T times the natural log of 1.065. So if we solve for T, it's going to be the natural log of 2 over the natural log of 1.065. So if you put that in your calculator, you get 11, basically 11 years. 11.01 years is the time to double at that interest rate, 6.5%. Let's do it with N equals 365. So I'm going to skip a little bit of the work and go straight to this part right here, because we're going to have the same numbers. 2,000 equals 1,000. So I would have 2 time to double, or the amount doubled, is equal to 1 plus 0.065 over 365, because we're compounding daily, to the 365, that's N times T. So basically I just skipped to the second line, because all of this would be the same, except it would be 365 and 365 here. Okay, so 2 is equal to 1 plus 0.065 over 365. If you put that in your calculator, that is 1.00018. Do not round that to 1, because that'll end up giving you you need to take it out until you get to at least a couple non-zero numbers. So we'll take the natural log of both sides. Natural log of 2 is equal to the natural log of 1.00018 to the 365 times t. Using properties of logs, you have natural log of 2 is equal to 365 times t times the natural log of 1.00018. Now solving for t, it's going to be the natural log of 2 over 365 times the natural log of 1.00018. I'm going to go ahead and put this in the calculator, put the calculator into view here, because we want to be careful. We've got the natural log of 2 divided by, I'm going to do a left parenthesis, 365 times the natural log of 1.00018, right parenthesis, and that is 10.55 years. So be real careful with your calculator on these problems, okay? Since you have to do a couple of, you might want to use parentheses, do something like that in the denominator. Okay, so takes less time to double when you compound it more often. Annually is 11 years. You cut off almost half a year if you compound it daily. Okay, so the homework for this section is on page 363. It's going to be 21, 24, 27, 29, 31, 33, 35, and 37. Not really any calculus in this. This is all pre-calculus, really. But it's good work. And I will talk to you on the next video.